Hi, I'm Steve Girvin. I'm a member of the Yale Quantum Institute. My office is right over here. I'm a theoretician, but I work very closely with the experimentalists at Yale and elsewhere on trying to design superconducting circuits for building quantum computers. So I'm giving the introductory lecture to this week course on quantum error correction, and I'm going to start with classical error correction so that we have the basic ideas down. We'll try to understand the difference between error correction and fault tolerance. And once we understand how to correct classical errors in the second half of this lecture, we'll do the simplest quantum error correction code. And that'll give you, hopefully the introduction that you need to understand the other lectures that you'll hear this week. So as Florian said, the key thing is for you to stop me when I say something you don't understand and ask questions. Don't be shy. There'll be other people grateful in the audience that you did stop me to ask the question. I'd much rather uncover a little than cover a lot, okay? So that you can learn something. Okay, so it's a pleasure to have you here, and let's get started on classical error correction. So the lectures I'm going to give are based on this tutorial article, which was based on lectures I gave in France. It's a fantastic summer school at Les Ouches, literally on the shoulder of Mont Blanc in the French Alps. It's available at this URL, and there are also videos of 3 of the 4 lectures that I gave. And I'll make these slides available somehow so you don't have to write down all the links. Okay. So it turns out that ideas of error correction and fault tolerance, which I'll define in a second, play a crucial role in 3 areas of classical engineering. In the 1940s, people began to develop control theory. You have a giant, plastics factory, and the machines have to do things in a certain order and not run too fast and not run too slow, and stop if there's some emergency condition occurs. And people were learning how to robustly control such plants, as they're called. And how do you control them when there's noise in the measurements you're making of the state of the system? Possibly even your controller is subject to errors. Okay. In the 1940s, Claude Shannon invented the theory of information, and he was working for the telephone company and was very interested in the resource cost of sending telephony signals, and today internet signals and digital cell phone signals. All the theory of communication was basically developed in a series of 3 papers. Just came out of the blue from Claude Shannon in the 1940s. And then in the 1950s, as computers were being built and John von Neumann, who defined the von Neumann architecture of today's computers, where you have a compute unit and memory and input and so forth. He was, in those days, they used vacuum tubes instead of transistors, instead of computer chips, and they failed very frequently. He was also extremely interested in how your brain works. You have this giant network, neural network, and neurons are signaling each other and somehow doing computation, and it doesn't seem to be designed, and it just seems to work, and as neurons die, your brain still can function. It seems to be robust against various biological errors. How can that possibly be? And so all of these areas benefited from people thinking hard about error correction, repairing the erroneous state of your machine, whether it's the bits in the computer or the elevator position in an Airbus aircraft. And then there's this deeper concept of fault tolerance, which is the ability to correct those errors even when the error correction system, which is also a physical system made of transistors or tubes or mechanical parts, and is itself making errors. So how do you correct errors when your error correction system also makes errors? That's fault. If you can do that, that's fault tolerance. Okay. So let's just go through those three examples. So control systems, you have a plant, sensors, controller, actuator, and feedback. And there's some input. For example, a standard example is automobile cruise control. You set the cruise control, you want to go 60 miles an hour. There's the engine, there's the speedometer, there's a little gadget that says, oh, I see the car's speedometer says I'm going faster than the set point I chose, so I should actuate the actuator to ease off on the gas to go back towards the intended speed. But possibly when my speedometer, has errors when it measures the speed, my controller might make a mistake when it's trying to figure out how to respond. The actuator that moves the gas pedal might have some kind of error in it. And so how do you build a robust cruise control or an aircraft autopilot or nowadays a self-driving car, right? You don't want anything to go wrong there, right? Okay. And then von Neumann was thinking about, how to make robust computers. And when he started, most computers were analog. They were based on either gears, or they were mechanical systems, or they were voltages that could vary continuously in some circuit. And you used a capacitor to integrate up the voltage over time to get some charge. That's how you did integrals. And digital circuits are much more robust against noise than analog circuits. So for example, here's a thing called a voltage clamp. And this appears in computer chips. It also appears in your brain in how neurons work. So if you have a noisy input voltage, the voltage clamp will convert it to a binary output. So here's the input voltage, 0 to 1 volt, say, and here's the output voltage of the voltage clamp. Anything below a half, the output is very close to 0, and anything above a half, the output is very close to 1. So if there's a little bit of noise on the input near 0.9 or something, nothing happens on the output. It gets rid of the noise. So you've paid a price. The signal only has two levels now, 0 and 1. But if I have 20 such bits, I can express levels between a million different levels, 2 to the 20 different levels. But each bit is now robust. Yes, sir?
Is there any advantage to not going halfway in terms of your logic? Why is the curve kind of near 0.4 versus maybe dead center?
Yeah, so you have to build a circuit that changes very quickly there. And there's some price to be paid in the complexity of the circuit or how fast it responds or something. As you make that steeper and steeper, it just gets trickier and tricky. So this is only to indicate that the output is actually continuous, but it jumps very, very quickly if you design the circuit right. And I just drew that by hand. I don't know how quickly they actually jump. Professor Samuel has his hand up.
Actually, for neurons, they are voltage gated, so you have to reach a certain threshold.
Right.
Once you reach threshold, it automatically goes off.
It fires, yeah.
And once you get up to a certain voltage, you begin to turn off gates, so then the flow of electrons across the membrane changes. So that's why it's not a step function. That's why it's gradual.
Yeah, I think it's more gradual in biology than in electrical engineering. Yes, you had a... Yeah, so to some you're trying to approximate a step function, right? There's reasons in biology that you may not want it to be a step function. People often take this sigmoidal response, and maybe that's slightly more realistic for neurons. Okay. And then von Neumann, thinking about computers where pieces fail, your brain where things can go wrong, started thinking about how to build redundancy into circuits, electrical circuits or neuronal circuits. You could have three entire computers, as is done in an Airbus, and the computers have to agree on the output before the plane automatically moves the control surfaces on the wings and tail, for example. Or you could have, this could be just some circuits inside a big computer, and it has many redundant parts inside, and there's some way of figuring out how to make it do the right thing even if one of the circuits fails. And I'll show you an example of how we do that. Okay, so really the understanding of fault tolerance in computation goes back to this guy, John von Neumann. Okay, so, and then Claude Shannon, so he figured out this idea in creating codes for communicating information reliably, even across a noisy channel. So nowadays, when you use the phone, everything is digital, actually. The analog thing from your voice is digitized, it's transmitted in packets that all take different routes to get to the other end. But when I was young, you picked up the phone and there was a wire that was connected from here to Seattle, and if you listened, you'd hear this sort of hissing noise from the various amplifiers in the background. And so then he started in the 1940s. So the idea is you have a message that you want to send, and you pay a price. You have to send a longer message with some additional auxiliary bits, and you combine those with an encoder that mixes up the message and the extra bits in some funny way. You send it through this noisy channel, and some of the bits are corrupted. Then you have a decoder, which looks at the bits that came and figures out what the original message was and figures out what errors occurred. Okay? And in your cell phone, there's specialized chips at the front end whose only job is to take in stretches of 100,000 bits and encode and decode on the fly very, very fast, things that couldn't be done before very fast computers were invented, because this is a big computational challenge. And it does this on the fly very fast. And the reason is that you need to do that is because, you know, your cell phone outputs a half a watt maybe, or 100 milliwatts, and the station may not be so close by, and there's interference and noise. A really great example is that some of the early satellites, like the Pioneer satellite that was launched, I don't know, more than 60 years ago, has left the solar system. It's way outside, beyond Pluto, billions of miles away. It's powered by solar panels, and it has a very tiny transmitter, maybe, I don't know, 10 watts or something, and it's billions of miles away. And so they actually reprogrammed it partway through its journey after new error-correcting codes were invented. They sent up a signal and just changed the operating system. And it sends back, now they're still in contact with this incredibly weak signal of, you know, I don't know, 10 watts or something that's coming billions of miles through the miracle of error correction. Okay, and what's interesting is that communication and storage, memory, are basically the same problem. In communication, Alice wants to send some bits to Bob, who's at another place in space. Memory is Alice wants to send a message to herself over time, and you know, a month later, she wants to have the same, get the message she sent, right? That's what storage and memory is. But it's, as far as Claude Shannon's concerned, it's the same problem. There's a noisy channel when you transmit this through space as a light wave or radio wave or something. There's a noisy channel when you put this on a hard drive, and cosmic rays are coming and flipping bits over time. It's the same problem, and it's solved by the same error correction techniques. Yes?
Can you go more in depth about exactly what a noisy channel is? Like, where's some examples?
Yeah, I will give you one very shortly.
Oh, okay.
If it's not satisfactory, ask again. Yeah.
Yes, sir.
But basically, the bottom line is Alice sends a 0, and it might arrive, and Bob might, maybe there was a voltage fluctuation or something happened, and Bob says, oh, that's a 1. He mixes up 1s and 0s. Yeah.
Is there anything nowadays that uses analog technology instead of digital?
Well, there are some hi-fi, maybe hi-fi doesn't even mean anything to anybody. There are some audiophiles who insist that vacuum tube amplifiers on vinyl, listening to vinyl discs, is the best way to do music. And there is analog electronics, but not so much. Still exists, I guess. I don't know enough about the current state of things to say much definitive there. Okay. All right. So you know, physicists believe that information is physical. It's stored in, carried by, represented by physical systems. For example, and the simple example is you have an electrical circuit with a battery, a light bulb, and a switch that can be in two positions. And the physical position of the switch can represent 0 and 1 because there's two values, open and closed switch. And if the circuit is closed, the light bulb will light, and the information which is in the position of the switch is now being transmitted through space, and anybody who has a light detector will be able to receive that same bit of information. Many people can receive that bit of information. That's not true in quantum mechanics. You can't copy quantum information. We'll talk about that no cloning theorem later. So there actually are two possible encodings. Who's to say that the light bulb off should represent 0 and the light bulb on should be represented by 1? You could do it the other way around. Doesn't matter. It's your choice. Okay? Is that clear? It's completely arbitrary. But Alice and Bob have to agree on what that choice is, right? And so Alice could be sending photons of light, pulses of light, to off, on, off, on, like that. And Bob and she have agreed in advance that when the light is on, that's a 1. And maybe that if none of the photons are lost or his detector fails to detect them or something, he will receive the correct bits. If they happen to, Bob didn't get the memo about what the Alice's convention was, he will get exactly the opposite set of bits, but no information is actually lost. It's all in there. All he's got to do, if it doesn't make any sense, is apply a NOT operation to every bit and see if that bit string makes sense. So the transformation law between the two possible encodings is just bit flip. If it's 0, make it 1. If it's 1, make it 0. And the information content is the same either way that Bob interprets the message. Now, what's interesting is that because there are these two choices, and only two, then really there's only one kind of error, bit flip. Now we're going to get to your question about what's a noisy channel. So basically, a noisy channel is one in which Alice sends a 0 and sometimes Bob receives it as a 1 incorrectly. Okay? It could be because something happened in the channel, or maybe his receiver has got some noise. Something went wrong. But the only thing basically that can go wrong is he can mistake a 0 for a 1 or a 1 for a 0. There's an asterisk here. There's another thing called erasure errors where one of the bits just fails to arrive. We'll talk about that later. But roughly speaking, the only thing that the noisy channel can do is flip a bit. A classical noisy channel can do is flip a bit from 0 to 1 or 1 to 0 some fraction of the time. When we look at quantum errors in the second half of the lecture, it's more subtle. There are more kinds of errors. Okay, so here's now the answer to your question. This is called a noisy binary classical channel. This was defined by Claude Shannon in the 1940s. So this represents two states. You could send a 1 or a 0. And if everything is fine, they'll come out the same as they were sent. A 0 comes out as a 0. A 1 comes out as a 1. But randomly, each time, this is a model that he made. The model is that randomly, each time you send a 0, there's a probability p00, it'll come out as a 0, and a probability p01, it'll come out as a 1. So you can think of this transition as a bit flip from 0 to 1. But if Alice sends a 1, there's a probability p11, it comes out as a 1, and a probability p10 that it comes out as a 0. Okay, does that make sense? And the smaller those probabilities are, the less noisy the channel is. Does that make sense? So, and as I said, ignoring erasures, there's only 2 possible errors. That a 1 becomes a 0 or a 0 becomes a 1. So these numbers, these 4 numbers, define the channel. And since a 1 has to come out as a 1 or a 0, the sum of those 2 probabilities has to be 1. And since a 0 has to come out as a 0 or 1, the sum of those 2 probabilities have to be 1. So there's really sort of only 2 numbers you need to define the channel, those 2 numbers there. Now, sometimes those numbers are typically they're not equal for various reasons. You know, it might be more likely that a 1 is received as a 0 than the other way around. But in the simplest case, the so-called binary symmetric channel, or BSC, then these 2 probabilities are equal to some number epsilon. So the probability that a 0 becomes a 1 is epsilon. The probability that a 1 becomes a 0 is also epsilon. That's a special case, but it's a little simpler to deal with, so that's the one we'll talk about. Is that clear? Okay. Okay, good. All right. Now for the asterisk, there can also be erasures. Let's say Alice has this flashlight, right? And she can send no light. That's a 0. Light is on. That's a 1. Well, you know, maybe sometimes a cloud passes in front, or there's Bob's detector doesn't work or something. Then he doesn't detect the pulse of light. Well, then he would think it's a 0. Okay? But maybe Alice can do something more clever. She can have a red flashlight and a blue flashlight. 1 is a 0. They're supposed to represent 0 and 1. But every time she sends a bit, there should be some light, either red or blue. But sometimes no light arrives. Then Bob knows something went wrong. That's an erasure error. The bit was lost in transit, you know? Okay? And so what's Bob going to do? He knows he was supposed to have received a bit at this moment, and he didn't. Well, the best he could do is like flip a coin and decide, just say, okay, it was a 0 or 1. Either that's correct, or it's the bit flip error that we talked about before. So when you lose bits, it's really almost the same thing as bit flips. And the nice thing is you know which bit not to trust when you're trying to decode the errors, because you know there's a 50% chance you guessed wrong on the bit. And you know which one is, in the long bit string, which ones are less trustworthy. And that actually helps you decode. And this has become, this concept of erasure errors has become very important in quantum error correction these days, and something we're actually working on. See? Is that, yeah.
So the equations that say like P11 plus P12 1, 0 equals 1, does that just mean they equal 100%? It's going to be...
Yeah, because if there aren't any erasures, if all the bits get through, a 1 is either going to be is definitely going to be received either as a 1 or a 0.
Yeah.
And so with 100% probability, you're going to get something as long as there's no erasures. That's what it means. Yeah.
So Steve, so when there are erasures, so then you're less than 1. So how do you, I didn't get that part. So how do you decide
Yeah.
which, is it a 0 or 1, or how do you even know?
You don't. So you flip a coin and put one of the values in there. And then it reduces to the same problem as before, bit flips. There's a little higher probability of bit flips because now there's bit flips that happened in transit and also erasures where you don't know what to do. So half of those are bit flips.
So could you also get information by building in redundancy in the signal like you did before?
Yeah. So we're gonna, you could send each bit 3 times, and if one of them doesn't get through and the other 2 are the same, chances are you know what the correct value was. We'll get into that. Other questions? Yes?
How would it validate whether you should have gotten 6 bits of information versus if it received 5? How would it know if you should have gotten 6?
Well, so maybe Alice and Bob have arranged that she's going every second, they have the clocks that agree, every second she's going to send 1 bit. And she's going to send a packet of 1,024 bits and then rest for 10 seconds and then do it again. They have some agreement, and then so he's expecting to get these on some regular schedule once a second. And if he gets 1 at this time and then there's 2 seconds before he gets the next one, then he knows he didn't get the one in between.
Okay, that was like for erasure. And and how does it validate if it should be a 0 or 1? If it does be 50% is correct, how does it know it's correct?
It doesn't. But the net effect is as if the channel was just slightly noisier and had a few more bit flips. And we're going to study how you can make codes that protect you against bit flips. Yeah, but we haven't gotten there yet. But you don't know what the bit is supposed to be, but you do know in the case of erasures which bit is doubtful. Yeah. Okay. All right, so before we do error correction, let's do error detection. I just want a flag to go up and say, hey, something's wrong. It looks like there's an error. You're going to have to stop and ask Alice to send it again or something like that. Okay, but you can't correct the error. And that's done with a duplication or a 2-bit repetition code. Okay, so every time Alice wants to send a 0, she sends 0, 0, 2 zeros. Every time she wants to send a 1, she sends the message twice, basically. Okay? It's not the greatest code, but it's the simplest code. All right, so here's what Alice sends, 0 or intends to send. Let's say we're just going to consider that she's sending a 0. And here's what Bob, what comes out of the channel. This is what Alice puts into the channel. This is what comes out of the noisy channel. Okay? Sometimes there are no errors, and 0, 0 comes out. Sometimes there's 1 error, and it was on the first bit. Sometimes there's 1 error, but it was on the second bit. Sometimes there are 2 errors, and both bits flip. Okay? All right. So what's the probability? Well, if P or epsilon, same thing, is the probability that a given bit flips when it goes through the channel, and I'm assuming it's a binary symmetric channel, then the probability that it doesn't flip is 1 minus P. And you have to have this guy not flip and this guy not flip. And when you have two independent probabilities and they both situations have to be true, then you multiply their probabilities. So you get 1 minus P times 1 minus P. Let's say P is 0.1. Then there's a 90% chance this guy won't flip, and a 90% chance that guy won't flip. And the probability that neither of them flipped is 0.9 times 0.9, 81%. Is that clear? Yeah. Okay. Then the probability that the first one flipped is P, and that the second one didn't flip is 1 minus P. And then this one has the same probability, it's just in the other order. The second one flipped, and the first one didn't, but those are algebraically equal. I should have written it the other way, but it doesn't matter. The probability they both flip is P times P. So if it's 10% for one of them to flip, it's only 1% for both of them to flip, so it's rare. Okay? Yes?
Now with the last one, now how would you be able to differentiate whether the input wasn't 1, 1 for you to get an output of 1, 1?
Excellent question. You can't. So this code cannot correct actually any errors. In particular here, there are two errors. That looks just like the Alice intended to send 1, 1, and there were no errors. So you would fail to even notice that that was an error. Okay? If the bits agree, you assume there's no error. But in fact, there could have been 2 errors. If the bits disagree, you don't know whether it's this case or that case coming from 0, 0 or from 1, 1. You can't. All you can do is say, I know one of them is wrong. I just don't know which one. So this heralds. You can use that to raise a flag and say, hey, something went wrong, but I can't tell you what the intended message was. Is that clear? But sometimes with low probability, like 1%, you get completely fooled. There is an error and you don't realize it. Okay? So this is, so 81% of the time, everything is fine. This is 9% of the time, the bits disagree this way or that way. So that's 18% of the time, basically, almost. And 1% of the time, you get completely fooled. Okay? But in no case can you correct the errors. But the most likely error when P is small is either 0 errors or 1 error. And if there's 1 error, the flag goes up and you say, I know not to trust the message because something's wrong. A small amount of the time, 1% of the time, I totally get fooled. I think there's no error. Okay? Good. Okay, so I'm getting some there's costs and benefits to doing this. I have to send the message twice, so my bandwidth or the rate at which I can send information is lower by a factor of 2. Bandwidth is just an electrical engineering term for rate at which I can send bits. I have to send everything twice, so I can only send half as many messages, right? The fidelity the fraction of the time that there's no error falls from 1 minus p to 1 minus p squared, because they have to, no error, you have to have both of those guys have no error. You have more bits, so there's more chances for error. So that's not so good. On the other hand, the unheralded error rate, that is, that there's an error and you don't notice it, is, let's say I just sent 1 bit. There's a probability p it'll be wrong, say 10%. But now the probability that I get completely fooled is only this case. That's only 1%. It goes from p to p squared. That's good. Yep.
Do these rules hold, like if you have 3 or 4?
We're going to do that next. Yes. And when you have more than 2, if you have an odd number, you can do majority voting, and that helps you correct errors. Good. Okay. So you still get lots of errors from this, but you know not to trust that, and you can ask Alice to send again or something. Okay? Okay. Good. So let's now go up to 3. And now you have, you can do majority voting. So here's what Alice, again, just wants to send logical 0. So 0, 0, 0. She's going to send it 3 times. So now, you know, the bandwidth is down by a factor of 3. It comes with a cost, but the probability of correctly decoding the message is now going to go up because you can correct errors. Okay? So this is what she puts in. This is what comes out. Sometimes there are no errors. That occurs with, I've switched from p to epsilon here. Sorry. 1 minus epsilon cubed, because all 3 bits have to be correct. Each is correct with probability 1 minus p or 1 minus epsilon. There are 3 different ways to have 1 error. Could be on this bit, or that bit. That occurs, and so it's each one is epsilon times 1 minus epsilon squared, because there's 1 with an error and 2 with no error. But there are 3 different ways that can happen, so there's a 3 there. There are actually 3 ways you can have 2 errors, which is a little funny, but if you think about it, one of the 3 doesn't have an error. There's 3 ways to do that. And it's now 3 epsilon squared, because there are 2 errors, 1 minus epsilon, because that guy, one of them doesn't have an error. And then there's only 1 way to have 3 errors. And you get 1, 1, 1. Okay, now let's do majority voting. So I go here, and I say, oh, all 3 of these tell me it's 0. It's almost certainly a 0. And you get the right answer, because Alice sent 3 zeros. Here, Alice sent 3 zeros, and Bob got 1 of these. But he looks at it and says, oh, 1 of these is different from the other 2. You guys all probably young enough to have grown up on Sesame Street, so you know about finding out which one is different than the others. So you say, oh, I'm going to do majority voting. 2 out of the 3 tell me it's a 0, so I'm going to go with 0 as the answer. And that's correct, because that's what Alice sent. Okay? So this is correctable by majority voting. Here, 2 of them are flipped, and you say, oh, I see 2 of them are 1. Probably the most likely thing is there was 1 error, not 2 errors. And so I'm going to decode this as 1, 1, 1. That's wrong. So the majority voting rule fails here, and it fails completely here because you don't even think there's any errors. But actually, it's a very rare situation where there were 3 errors. Okay? But, and again, the probability of no errors has now fallen because I'm sending 3 bits, each of which can have an error. But the most likely errors are the ones with only 1 error if epsilon is small. And I can correct those. So now I'm winning. Then it's, I still fail if there are 2 errors. But that only occurs with an epsilon squared as for small epsilon. That's the most important thing. And occasionally there's 3 errors. So this would be 1% of the time. This would be 1 time in 1,000, say. Okay. So the probability of an uncorrectable error, that is, there are 2 physical errors or 3 physical errors. Because it's an or, you should add the probabilities, not multiply them like you do when it's an and. So that's in the limit of okay, actually, if you just add these 2 terms, you get this: 3 epsilon squared minus 2 epsilon cubed. If epsilon is, 1%, this term's a lot bigger than that term, so it's approximately 3%. Okay? So if you sent 1 bit, let's say there's a 10% chance of getting an error. But now, after you've corrected these errors and are only fooled by 2 or 3 errors, the probability is closer to 3%. 3 times 0.1 squared plus minus a small correction. So you're doing better by about a factor of 3. So you can make this plot. This is the error probability per bit. If I just, and here's the logical error, that is after the decoding and fixing any errors that you can fix by majority voting, what's the probability you got it right? Well, if you just send 1 bit, it's just equal to the physical error probability. But if you use this 3-bit error correcting code, you get a result that looks like this. And below an error rate of 1/2, the logical error rate goes down relative to just sending a single bit. So you pay a price. You have to use the channel 3 times. You can't send messages as fast, but you receive them more reliably. And way down here, it's much more reliably, because the probability of getting fooled starts with 3 epsilon squared. So if epsilon is 10 to the minus 6, that's 3 times 10 to the minus 12. You're really gaining. Whereas this would be 10 to the minus 6. So you gain 6 orders of magnitude. Okay, so that you can define what's called error correction gain, and we do this in quantum error correction also. That's where we first defined it, actually. It's the physical error rate on each bit divided by the logical error rate, the thing that when Bob does the decoding and corrects the errors, what's the probability that he got it wrong? If this is bigger than 1, that's good. You have error correction gain. So it's the ratio of this number to that number. Does that make sense? So that ratio gets huge way down here. It's very close to 1 at what's called the threshold, or the break-even point. Okay? So if I just divide out powers of epsilon, I get 1 over epsilon times 1 over 3 minus 2 epsilon. If epsilon is small, I can throw that term away compared to the 3. It's approximately 1 over 3 epsilon. So it's really getting big for small physical error rates. So, and this is an important lesson. Errors are much easier to correct if they're rare. But there is a price, a 1/3 there, because I've got 3 bits and each of them can have errors. So there's roughly 3 times as many errors as before, but most of them are correctable. Okay? So if this is 10 to the minus 6, that's 1/3 of a million is the gain. It's a huge gain. So errors, uncorrectable errors are very rare. Okay? Okay. So now, well, that was good. Why don't we make a repetition code with 5 or 500, and get really, really sure. So, so we have to take an odd number so that there's no ties. So we'll say the number of bits is 2m plus 1. The code encodes 1 logical bit. I send a string of 51 bits, say, and I can decode and get 1 logical bit out of it. That's k. There's a thing called the code distance. The code distance d is the smallest number of errors that are needed to completely fool you, because it takes you from one code word to the other. So here I have a 5-bit repetition code. If Alice sends 5 zeros and there are 5 bit flips, then it looks like there are no errors. Okay, so the code distance is the number of bits in this case. And there's this standard notation, NKD. N is the number of physical qubits, K is the number of logical, bits, and D is the distance. Okay? So this would be a 515 code. Okay? Now, when you have 5 bits, the majority, you can correct 1 bit, 2 bits flipping. But if you have 3 bits flipped, then the correct bits are now in the minority, and the majority voting is going to get the wrong answer. Okay? So that for when D is odd, that's the minimum. If the number of errors is D plus 1 over 2, so 5 plus 1, 6 over 2 is 3. If I get 3 errors, that's now the majority, and I'll be fooled. Okay? So it turns out that then for very small physical error rates, the logical error rate scales like this. You need at least D plus 1 over 2 errors. And when epsilon is small, the most likely thing is that you have D plus 1 over 2 and not more. And then there's some big combinatorial factor in front, because there are many different ways to distribute those errors over the bits. It could be in the beginning, in the middle, the end. There's some giant combinatorial factor. Okay? But again, the bigger the distance, the smaller the physical error rate, the better you're going to do. Errors are easier to correct when they're rare. Okay, so let's go back to our triplication code, just n equals 3. Here's the code space. This is 000 is a legal message. 111 is a legal message. Anything else is an error, right? And but part of the space, let's say where there's 1 bit flipped, that's still correctable. But if there are 2-bit flips or 3-bit flips, you're out here in what used to be on ancient maps, here be dragons. You're going to get fooled if you're out here, or eaten by the dragons, right? So the error correction circuit, its job is to put you back here in the correct place that you came from. If it came from 000 and had 1 error, you should put it back there, not there. If there are 2 errors, out here, then you're going to put it back and get the wrong thing. So so that's error correction. Let's again talk about fault tolerance for a second. So this is either a control problem or a communication problem, and this is the good place. This is where the number of errors is correctable, or the autopilot can recover from turbulence if it's not too big, and out here you can't. Okay, and in the example of the 3-qubit repetition code, this is the space that has 0 or 1 physical errors. This has 2 or 3. And so you could have errors on the data qubits. I haven't shown you yet how you do the decoding, but you need some extra circuits, some extra bits to do that. They could have errors. You could be part of a computer. You're doing operations, NAND, XOR, AND, whatever, on these bits, and maybe those gate operations produce errors. But as long as they're not too bad, like they're still correctable errors, it's not so terrible, because maybe the system will correct the error in the next round. Then you have partial fault tolerance. But suppose that you get some kind of something happens that causes errors to spread. So now you have 2 errors because you did some gate operation. Then you fail. You're not completely fault tolerant. Okay. So let's make this more concrete now. Here's my 3-bit repetition code. And I said, we just do majority voting. No problem. It fixes most of the errors. Well, how do you do majority voting? You got some kind of little computer widget, circuit widget, which I'll just call MADGE, that compares the 3 and outputs whatever the majority number is, 0 or 1. Okay? Well, that's not fault tolerant. It can correct 1 error here successfully, but this is a single point of failure. That little piece of the circuit we were assuming didn't cause any problems. But when you are dealing with fault tolerance, you have to be very paranoid. Everything causes problems, and this unit could fail. It could have some noise or something. And then maybe the majority is supposed to be 1 and it outputs 0. Then you end up with 0, 0, 0, and it's wrong. Okay, so there's a single point of failure. Well, you can make it tolerant of one of the, you can replicate the majority voting units, okay? We're going to assume all the wires don't break. We've got to assume you can't be completely paranoid. So here's your code, right? 3 bits, and you copy them into all 3 majority voting units. Okay? And then each majority voting unit votes and outputs here. If one of these should fail, the majority, you're still inside the correctable space. You'll have like 0, 0, 1. When it was supposed to be 0, 0, 0. Okay, so that's an error, but it's correctable. And chances are, when you run this again, it'll get repaired in the next correction round. Okay, so that's an example of partial fault tolerance, where you're tolerant of a certain number of errors in the form of bit flips, and a certain number of errors in the circuit that corrects the errors. Yes?
How's this all that different from just error correction with 9 bits?
Well, if you had 9 bits and 1 majority voter circuit, this is a single point of failure. If you had 9 bits and you had 3 copies of this, you could be tolerant of one of those failing, because 6 of the 9 would still be correct. There's some subtleties over which one is better. I have to think about it. I think this is actually better, but I'd have to think about it.
I have a question.
Yeah.
We have a layer of majority voting and a figure B. Like, can we repeat it multiple times as in a neural network?
Yes. You guys are great at asking questions. So let's do memory, okay? So I'm going to encode in 3 physical bits. I'm going to check for errors, and then I'm going to wait. That's my memory. I'm storing it, okay? Then I'm going to repeat. After some length of time, I'm going to check for errors again every few seconds or something. And now, you know, what is the epsilon that you put in there? Well, there's an epsilon m for the probability one of these guys fails. But there's an epsilon for bit flips just while it's sitting there idling, cosmic rays coming or something. And that probability grows with time. So the longer I wait, the more likely there's going to be an uncorrectable error, 2 errors or 3 errors here. So I don't want to wait too long. On the other hand, if I don't wait very long and I keep applying these things and they cause errors, that's not good either. And it turns out that the optimal length of time to wait to check for errors and correct them, when the correction is good but not perfect, you should wait until the probability of an uncorrectable error here is about the same as the probability of an uncorrectable error in the majority voting segment. And so as a function of waiting time, at short times, you're checking so often that most likely you're causing errors by checking and one of your majority voters is messing up. If you wait for long times, the error rate goes up because you're dominated by bit flips that are occurring in between the error checks. And there's an optimum where the probability of a physical error and the probability of a majority voting error are about equal. Okay? All right. You can also do fault-tolerant gate operations. Here's a NAND gate. Yeah.
Go back to the last. So is this going to be system or platform specific?
Absolutely. Absolutely. So for example, good. So superconducting qubits don't do very well in the idling part. They have errors much more frequently than trapped ions or Rydberg atoms. Okay? On the other hand, we have extremely good gates. So we don't tend to make errors during gate operations like AND and NAND and XOR. So we have to have error correction just for memory. Whereas a cold atom system that has a coherence time of 1 second or something, it would be very hard to get any error correction gain for memory because the memory is already so good. But they have a huge problem because their gates are slow and not very good. Now, why is that? Because the reason they have 1 second coherence times is that their atoms are almost disconnected from the rest of the universe, including your control system. There's this sort of iron law that if your qubit has good coherence, it's because it doesn't couple to the environment or to you. So there's this like engineering conundrum that we're all trying to do error correction. They're trying to do it after gates. We're trying to do it between gates. Yeah. Good. So here's some NAND gate where the output is not A and B. And you can triplicate those circuits, throw in and work in this encoded basis of an error-correcting code for each wire. And there are 2 wires in and 1 wire out. And I won't go into the details here, but this is how you would do this in a classical circuit. Okay, time for a break. Okay, so you have the background now on the simplest classical error correction code, just a repetition code. It's not very efficient. If you want to have a 101-bit repetition code, you have to use the channel 101 times or use 101 channels, and you're still only sending 1 bit. So there are much more sophisticated classical codes, but likewise for quantum error correction, we're going to use a quantum version of the simplest thing, a repetition code. But there are lots of subtleties that are different than in the classical case. So let's start with a quiz. Is quantum information carried by waves or particles? Yes. Is it analog or digital? Yes. Okay, you guys catch on quickly. So it's pretty different and weird. And one of the weirdnesses is the superposition principle. So if I have a register of n, let's say 3 classical bits, the register can be in one of 2 to the n possible states, either this one or that one, representing the binary numbers in this case from 0 to 2 to the n minus 1, 0 to 7. But a register of quantum bits can be in an arbitrary superposition of all of the states with arbitrary coefficients, complex coefficients in front of them. And so if you want to represent the most general quantum state of even a small quantum computer with, say, 50 bits, the state space has 2 to the 50 basis vectors in it, and each one can have some arbitrary complex coefficient in front of it. 2 to the 50 is around, 2 to the 53 is about a petabyte, 10 to the 15 bytes, which is pretty big. And there are tricks for approximately representing things, but you can see that it doesn't take a very big quantum computer before it becomes difficult to fully simulate classically, which is part of where some of the power comes from. But this huge information content of quantum superpositions comes with a cost. It's great sensitivity to noise and perturbations and dissipation. All that quantum state, that superposition, is very delicate. And that's why we're going to need quantum error correction. So, for example, the phase of the complex numbers in those superpositions tend to be well defined only for some finite, what's called coherence time, T2. And so, but despite this sensitivity, we've made exponential progress in the last 20 years in terms of superconducting qubit coherence times. As I mentioned, atoms and ions are very coherent. They can remember what state they're in for seconds. That's why we use them for atomic clocks. But with superconducting qubits are many orders of magnitude worse, but getting better, exponentially better over time. When the first superconducting qubit was made by Nakamura in Japan in 1998, it had about immeasurably short coherence time, maybe around 1 nanosecond. And now we're up this is a little old plot here, but we're up to millisecond coherence times, so 6 orders of magnitude gain, just by engineering better materials, better qubit designs, better what we call microwave hygiene, all kinds of just, engineering things. And, but no matter how much progress, yes?
Sorry, could you explain T1 versus T2?
So T1 is, so typically you have some kind of artificial atom like a superconducting circuit or a natural atom, and you take, and they have quantized energy levels, and typically you take the lowest two, but not always, to be your 0 and 1 of your qubit. And if you're in 1 and you're an atom, you could fall down to 0 and emit a photon of light. Hydrogen does that in about 1.5 nanoseconds. A transmon superconducting qubit does it in free space, does it in about 100 nanoseconds. It doesn't emit an ultraviolet photon like hydrogen, it emits a microwave photon. But if you surround it by a superconducting box, you can make it live, makes it hard to emit that photon, and it can live for milliseconds. So the rate at which the state relaxes from 1 to 0, or heats up from 0 to 1, but typically it's downhill. That rate is called 1 over T1. Okay, if you have so that's 1 goes to 0. If you have 0 plus 1, and the phase of the superposition changes to minus in some length of time, the rate at which that happens is called 1 over T phi, the intrinsic dephasing rate. And for complicated reasons, there's a thing called 1 over T2, which is 1 over T phi plus 1 over 2 T1. The phase might not be changing, but if you collapse from 1 to 0, the superposition is gone. So there's sort of T1 contributes to the loss of the superposition because it stops being a superposition, and T phi contributes to the loss of the superposition because it messes up the phase. And it just turns out that 1 over T2 is that particular quantity. Good. So yeah, if someone says, tells you about T1 when you ask them what the coherence of their qubits is, walk away, because T1 is not really it's T2 that counts. Okay, other questions? Okay, so we keep making physical progress with better materials, better qubit designs, more isolation, and the coherence times are getting longer and longer. So far, about 6 orders of magnitude longer in superconducting qubits. But it doesn't matter. You still have to deal with the iron law of quantum computing. There's no such thing as too much coherence. If you get your quantum computer to run for 1 second, somebody will say, some computer scientist will come and say, "Oh, please make it 2 seconds because I need my algorithm to run longer." There's just no limit. And so we need quantum error correction. We've gone a long way with reducing the physical error rate, but now we're beginning to study quantum error correction to reduce the logical error rate by taking many physical qubits, making logical qubits, and executing quantum error correction. Right.
When we talk about a fault-tolerant quantum computer, then given what you just said, you said we will never develop quantum qubits that would maintain their coherence.
Yeah, we will never build. Some people think that when you have fault tolerance, you have immortal qubits. No, there's only partial fault tolerance. Like, it's almost impossible to be tolerant of somebody tripping over the power cord and disconnecting your computer, you know, or some other correlated errors. You can make the error rate lower and lower, and fault tolerance means that when the error rate gets really low, you need your error correction circuit to really not make errors, or it'll be the dominant source of problems. That's what fault tolerance is, roughly speaking.
So the error will never get to zero asymptotically.
Yeah, it'll get exponentially small if you have a fault tolerant design, but exponential in the number of qubits you use, technically exponential in the so-called distance of the code. Nathan.
Just as a clarifying little point about this, there's an issue that actually is also really fundamental about this, because what you want is you want to also be able to control your quantum bits. So the problem is that you need to kind of build this magic box, right, that you can figure out a way to manipulate the quantum information inside, but the noise processes in your environment can't figure out that secret that you're using to manipulate the information.
Yeah.
And that's one of the reasons why there's always going to be, at some level, errors that will come in from the environment.
Right. If you want to lock your qubits up in a safe and protect them from the environment, that's great, but you'll never measure them, you'll never do gates on them, you know. So that's the engineering challenge. Good. Okay. And I've already given this point that we need error correction for memory in superconducting qubits and error correction for gates in other platforms. But we still need error correction. Okay. Now, quantum errors are more subtle, like everything in quantum mechanics is more subtle than classical mechanics, including the errors. So here, let's just consider one bit. It's in a superposition of 0 and 1 with complex coefficients alpha and beta. And let's say there's a bit flip error. So I apply a Pauli X, and not me, but the noise demon applies a Pauli X and flips the bit. Then it goes from alpha 0 plus beta 1 to alpha 1 plus beta 0, right? The superposition, it's in a superposition state, but the bit flip works on every element of the superposition if there's that one bit. If you have a phase flip, alpha is still multiplying 0 and beta is still multiplying 1, except the sign of beta flips. Okay? You could have both. Well, that's a Y error, because the Pauli Y matrix is I times XZ. So that's a global factor of the complex number I, but it doesn't affect anything typically. You can have what are called coherent errors. Suppose I have my qubit on the Bloch sphere. It's supposed to be here, and the noise demon just rotates it a little bit over this way around the x-axis. Well, that's given by this operation, which is a superposition of the identity doing nothing, some complex number, and a bit flip. So did the bit flip or not? Well, it's in a superposition of having flipped and not having flipped. You need to be able to fix those kinds of errors too. Okay, that's pretty weird. Then there are these non-unitary errors like amplitude damping, where 1 can decay down to 0, but maybe the reverse can't happen, or maybe it does, but it's a separate process. Maybe there's photons running around in your environment because it's hot and they can excite the qubit. Okay, that's another kind of error. So there are lots of these kinds of errors, whereas in the classical case we said ignoring erasures, there's just bit flips. Okay? The simplest ones to understand are these Pauli errors, X, Y, and Z. But that's not, necessarily realistic, and these other kinds, which are harder to deal with sometimes, you can't ignore them just because they're harder. They do happen. Okay, so here's the error correction problem. Oh, sorry.
Just to be clear, erasures can happen in quantum too, right?
Yes, we are in the business here of designing codes where you can tell when it leaks out of the code space, and the qubit you can make a measurement that raises a flag and tells you there's a problem with this particular qubit. But I'm not going to go into that here. Okay. It does have a number of advantages. Okay, so here's the error correction problem in a nutshell. I'm going to give you a qubit in an unknown quantum state. I'm going to pluck it out of the middle of my quantum computer. It's in some weird superposition state. It's probably entangled with 130 other qubits in my processor. I have no idea what the state is. If you measure it to see what state it's in, the state will collapse to whatever it is you see, right? If you measure, are you in 0 or 1, it will come back and say yes every time. I'm in 0 or I'm in 1. And the state has changed in a way that you can't tell. So if it develops an error, please fix it. Well, you have to measure something to see what the error is and fix it. How in the world can we do that? And amazingly, it can be done. And you just have to be very, very subtle in what you measure and how you encode the information in a clever way so that you can learn what error happened, but not learn what quantum state the logical qubit was in, because then you would collapse it. Okay? Once you learn what error happened, let's say, oh, there was a bit flip on qubit 7, then I just apply another bit flip and it's fixed. That's the idea. Yes?
So does this mean that for an unknown quantum state, you can't make an exact copy of it?
Yes. We'll come to that. Okay, so pictorially, we're going to create a logical qubit out of some number, in this case 9 physical qubits. And we've got to encode, the logical qubit is, a qubit is in alpha 0 plus beta 1. The quantum information is in the coefficients alpha and beta. And somehow that information about alpha and beta has to be hidden inside here in some clever way, in some giant entangled state. The information is in the correlations among all these qubits. It's not in any single qubit. Because if it were, then the environment could measure this somehow by some decoherence or decay process, could measure the state of that, and then it would learn the state of the logical information, and then it would be dead. Okay? So there's some non-locality. And then you need an error correction gadget, which I'll call a Maxwell daemon, that from the statistical mechanics, that is making these very subtle measurements to locate the errors and correct them, and pump the entropy or the randomness out of your quantum state into some cold bath, just the way heat flows from hot to cold in thermodynamics. And we talked about this in the classical case. If you have n qubits, each one is having errors. So the error rate, first thing that happens is the error rate goes up by a factor of n. You take a giant step backwards. There are now many more errors than when you just had one qubit. So they're paying a big price. And the Maxwell daemon has to be so fast and clever and accurate and looking for the errors and getting rid of them that it overcomes that factor of n and then you get back to where you started, then it has to do even better than that if the error correction gain is going to be bigger than 1. Because the error correction gain is the lifetime of the logical qubit divided by the lifetime of the best single quantum component, a qubit, inside, the best physical one. Okay? Just because you turn on the error correction and it gets better doesn't mean that you're gaining, because you have to get past that factor of n just to break even. Okay? This is why it's very, very hard. Okay, so yeah, so that's error correction gain. It's the same thing as we discussed in the classical case. So quantum error correction is a kind of emergent or collective phenomenon, much like a phase transition, like between a magnet being demagnetized and magnetized is a phase transition, or water turning to steam. It really, in order to get an immortal qubit, you have to take the limit of an infinite number of physical qubits inside your logical qubit, which will never happen, but you can get close. So weirdly, you know, among all these physical qubits, one is better than all the others. And you have to beat that. And by adding n minus 1 not as good qubits, but then doing something collective with them, you can make it better than the best one. Okay, so let's start with a quantum version of the repetition code with 2 qubits. The one we looked at classically, right? We could herald errors, but we couldn't correct them. So let's do the same thing here. So here's my my unknown quantum state. I'm writing it here as the alpha and beta, but we don't know what those are. And then I'm going to do some unitary circuit with C naughts and knots and Toffolies or whatever gates, and I want to take this state and copy it into an ancilla that's initially in 0. So I want to go from here to here. And this is the thing that's impossible. Somebody asked about that earlier. If you know what the state is, you can just follow the same recipe that you used to create that to put this in the same state. But if you don't know what those are, it's impossible, and that's the no cloning theorem. How does it work? Well, quantum mechanics is linear. This is just some big matrix acting on this state vector. And if you don't know what alpha and beta are, you can't make that big matrix depend on alpha and beta. It's just a bunch of numbers. But look over here on this side, you see there are some coefficients, like the state 0, 0 has coefficient alpha squared, or beta squared, or alpha beta, that are not linear in alpha and beta. So something's wrong. I'm doing linear algebra, I'm multiplying this vector by something that depends linearly in alpha and beta by a big matrix, and getting something that depends non-linearly on alpha and beta. That's impossible if you don't know what alpha and beta are, so that you can put those numbers inside U. So that's the no cloning theorem. Equivalently, if I give you an unknown state and you want to copy it, you should have to measure it in order to make a copy to see what it is. And when you measure it, it changes. So that's the physicist version of this is an incredibly simple argument, but it wasn't made until the 1990s, I think, and was a huge big deal when people, it's one of those things, darn, I wish I had thought of that. It's incredibly simple, but profound. Okay? So there are no quantum Xerox machines for unknown states. Nathan wants to say something.
Okay, yeah, I want to say something, but I was going to avoid it.
Feel free. Okay.
All right, fine. It turns out actually there's a classical effect to this too. We can't actually clone classical information either. sense that, if you imagine what you had is you had the ability to clone an unknown probability distribution. If you could clone an unknown probability distribution, we wouldn't need to poll the entire United States during an election. All we'd have to do is randomly select one person over the entire country and then clone that person's response before we look at it 1 billion times. And then we would actually have more information about the US polling preferences than we would by asking everyone.
Whoa.
If cloning classical information were possible too. So actually this is more general. It it's more to do with the probability theory
Yeah.
actually than anything about quantum.
I see. Interesting. Thank you. Okay. So we don't clone, we entangle. Instead of making this times this, we're going to make this. Right? Now alpha and beta only appear linearly on the other side. That's legal. Okay? And in fact, here's the circuit that does it. So here's my unknown state. I don't know what it is, but I apply a controlled knot. So for this part of the state, the control is in 0. So nothing happens here. It stays in 0. For this part of the state, the control is in 1. That activates the knot operation here and puts the ancilla in 1. So you end up getting this entangled state, 0, 0, plus 1, 1. All right, that's just simple C-knot circuit. And that produces this duplication or 2-bit repetition code state. Okay? We don't know whether the bits are 0 or 1. We just know they're the same. Right? And so if they're somehow not the same, there's been an error. Just like in the classical case. But how are we going to figure that out? So I need to measure what's called the joint parity operator of these two qubits. Z for the first qubit times Z for the second qubit. If for state 0, 0, that would be, this will give +1, that'll give +1, so I get +1 times the same state. Here they're the same. I get -1 times -1. That comes out plus. But if they're different, one of them gives me a minus sign. I don't know which one. Okay? And so if I were able to measure this quantity, I would get 1 bit of information. If it's minus, there's a single bit flip error. I don't know where, though. So this operator has eigenvalue +1 and -1, just like a Pauli matrix. So you can somehow measure it by mapping its value onto a qubit and then measuring that qubit. Okay, what you do not want to do to measure Z1 times Z2 is measure Z1 and measure Z2 and multiply the results. Why? Because if I'm in this superposition and I measure just Z1, never mind Z2, and I get +1, this part of the state's inconsistent with that. It collapses away because that would have given -1. And so I lose alpha and beta. I just get 0, 0. The state changes. If the measurement result is -1, it collapses to this. And again, I've lost alpha and beta. If I measure each of these, I get 2 bits of information. That's much more than I want. I want only 1 bit. Which of these 4 things am I in? But whether the bits are the same or different. That's one bit of information. Okay? So this is a very important distinction. Just as, by the way, I always get these questions when I teach this circuit, like, so controlled knot. So this guy measures the first qubit and then decides whether or not to flip this one? No. It has to work in superposition. If it were to measure the first bit, it would collapse. Okay? So it has to be something more subtle. Okay. So it's not so easy to measure this weight 2 operator, this product of two Pauli matrices. A more natural coupling would be that, like, these represent maybe nuclear spins or electron spins, and they couple to some external magnetic field by the sum, not the product. The states 0, 0, and 1, 1 are very different. There's much more energy in this state than that state, and yet this operator treats them as the same. It can't tell the difference. So I got to do something very clever to learn whether they're the same without learning what state they're in. Is that clear? Okay, so you have to have clever experimentalist friends. But if you're a theorist, you do it like this. Okay, so here's your encoded repetition code, and then you have an auxiliary measurement qubit. The thing you want to measure, Z1, Z2, has only two eigenvalues, +1 and -1. If I could map those onto the Z of that qubit and measure that guy, I would learn only the product and not the individual things. So I do that with encoding with two controlled knots. Okay? So if both of these qubits are the same, if they're both 0, let's say, then neither controlled knot is activated, and this comes out to be 0. If both qubits are the same and they're both 1, then both gates are activated, and this gets flipped twice, 0 to 1 to 0 again. So if this comes out 0, you know they're the same. If they're different, if you had 0, 1, for example, then this would not flip and this would flip, or the other way around. So it flips. If they're different, one of the two gates flips you, and you end up in 1. So now I've mapped Z1, Z2 onto the Z of this guy, and the state becomes 1 minus the product of the Z's. So this is, if they're the same, this is +1. 1 minus 1 is 0. I'm in state 0. If they're opposite, this becomes -1, and I get 1 minus -1, which is 2, divided by 2, 0, is 1. Okay? Is that clear? So by this clever circuit, and the fact that you can't tell the difference between flipping the ancilla 0 times and 2 times, I lose the information about what the individual bits are on these wires. Only their joint property is left. Okay. All right. So let's look at again, this is a duplication code, not a 3-qubit code, so it can't correct errors. Just like the classical case, it can only herald the errors. So let's consider a coherent error on the first qubit. That's the 0th qubit, that's the first qubit, maybe. Or first and second, I don't care. That's the first, okay? So I'm going to coherently rotate. I'm not, but the noise demon is going to coherently rotate the first qubit a little bit, and I'm going to get a coherent superposition of no error and bit flip on the first qubit. Okay? So I don't even know if there's an error or not. There might not be, or there might be. Okay? So I end up with this state, cosine theta over 2 times the original state plus I sine theta over 2 times the original state, except the first bit has been flipped. Is that clear? Okay. So now I measure Z1, Z2. Okay. If it comes out positive, the error goes away. It collapses away, and I end up in the original state. If you measure and see no error, there is no error. And you don't even know that the act of looking made the error go away. But it did. Does that make sense? If, on the other hand, and that occurs with probability cosine squared theta over 2 by the Born rule, but with probability sine squared theta over 2, the product of the two z's comes out to be negative, and the state collapses to this. The alpha and beta are still there, but they're multiplying different states. And now, there's no more superposition of no error and error. There's definitely a full bit flip error because you measured and there it was. The act of measuring brings the error state into existence, so to speak. Okay? So that's fine, but I don't know which bit flipped, so I can't correct the error. I only know there was an error, just like the classical code. Okay? So quantum errors are continuous. The noise demon can continuously rotate me on the block sphere. But this detector, this so-called stabilizer measurement of the joint parity, when I measure it, I get a discrete result. Either there was no error or there's a full error. And this, the measurement back action makes the error state discrete. No error or a full error. And this, the fact that quantum mechanics is both continuous, analog, and digital is what saves you from the no-go theorem that you can't do error correction in analog computers. Every position of the gears is a perfectly legal one, so how do you, if one of them got moved, how do you tell? It's this discreteness of your ability to make clever measurements that collapse this error state onto something definite that you can fix instead of being continuous that you can't fix, that makes this go. Yep.
If there's always noise, does that also mean that there's always going to be error after a measurement?
So if you measure this and you see no error, and then you just wait a little while, errors will creep back. If you measure and you see there is an error and you fix it, errors will again start to creep back in. Unfortunately, it takes time to measure and fix, so errors can happen while you're doing those things. And that's where you have to get into fault tolerance, and it's more complicated. Okay, so now let's do the error correction, just like we did in the classical case with a triplication 3-bit repetition code. And instead of creating it with one C0 to flip one ancilla, I'm going to have two C0s to flip two ancillas. And I'm going to make this state alpha 0, 0, 0 plus beta 1, 1, 1. Yes?
Two questions to make sure I'm understanding your diagrams right. Here, you're using one register for what was two registers in the previous diagram. I think like you had two lines and you had the C0s connected in. Oh no, sorry, you haven't entangled yet.
No, this is the entanglement. So
like here.
This one was for the measurement. The third one was a measurement qubit. But now we have the original bit and two extra ones that we're going to entangle with it to produce the code word. And then to measure things, there'll be more ancilla bits.
For the production.
Yeah, right. So that produces the code word, alpha 0, 0 plus beta 1, 1, 1. Good. Yes?
I noticed the formula down there. it shows me alpha 0 states and beta 0 states times 2 0 states, right?
Yeah.
And that turns it to be everything, which is alpha free 0 states and beta free 1 states.
Yep. So I'm applying this circuit. If this bit is 0, neither of these flip. If this bit is 1, both of these flip. So they end up being the same.
Oh yeah, that's a C NOT gate, right?
Yeah, yeah,
Okay.
yeah, yeah. So again, we don't know whether the bits are 0 or 1. We just know they're all the same. And we don't want to know whether they're 0 or 1. We just want to know if somebody's not the same as the others. Okay, so now, and just to be fancy, so here's 0 logical, here's 1 logical, here's the logical X operator. You just flip all the bits and go from 0, 0, 0 to 1, 1, 1. That takes you from 0 logical to 1 logical or back, just like the X Pauli operator. For a single bit, Z, you can just take Z, Z, Z. And for Y, you just take I, X, Z. And these logical operators obey the same Pauli group relations and algebra relations that single qubit Pauli operators do. But now we have 2 stabilizers, 2 joint parities, Z1, Z2, and Z2, Z3. I could also define Z1, Z3, but that's just the product of these two. It doesn't give you any new information. So I can use these to ask the question, are these two the same? Or are these two the same? Okay? Just like I did in the duplication code. And the code words are +1 eigenstates of each of these stabilizers or joint parities. Okay? Because I get +1 times +1, if I were to measure that, -1 times -1 for that. So they're +1 eigenstates. Okay? So if I measure these quantities and they're both +1, I know I'm in the code space. Okay, so let's look at the possible errors. Well, there could be just the identity error. That's our favorite error because nothing happens. This code can correct 1 bit flip, by the way, nothing else. The first flip, the first bit could flip, the second bit could flip, or the third bit could flip. If that happens, what happens to the joint parities? Well, if nothing, there's no errors, they're both going to be +1. If, let's say, the first bit flips from 0 to 1, then when I measure the joint parity here, it's going to be -1. And when I measure the joint parity here, it's going to be +1. Okay? If the middle bit flips, they're both going to be -1 because those two are different and those two are different. If the third bit flips, then the first parity is plus and the second is minus. Okay? So I'm measuring 2 quantities. That gives me 2 bits of information, and it allows me to uniquely distinguish among the 4 possible error states. No error, or one of the 3 bit flips. This is very important kind of counting arguments that you should get enough information out of your measurements to determine what the error state is, and no more and no less, right? So it's very convenient that there are 4 error states and I get 2 bits of information. And log base 2 of 4 is 2. Okay? So once I figure out which error happened, I don't know if it happened in the 0, 0, 0 or 1, 1, 1. All I know is that the middle guy is different than the other 2, so I should flip it back. So once I figure out which error happened, I just apply the same error because x squared is identity, right? If you flip a bit twice, you go back to the original state. So the noise daemon flipped the bit. I go in and flip it back. Is that clear? That cancels the original error. Well, but again, just like in the classical case, if there were 2-bit flips, so this went to 0, 1, 1, then I would say, oh, this parity is good, they're the same, and that one's off, so it must be the first bit that was wrong. And so I take this to 1, 1, 1. Now I'm done for. I made a mistake. Okay, majority voting failed. Likewise, with 3-bit flips, I would say, oh, there's no errors at all. I'm just in the other code word. Okay, so that code can only correct bit flips. But there's a related code that can only correct phase flips. And so I'll just remind you of some notation. So plus and minus refer to states that are in the plus and minus x direction on the block sphere. And they're 0, plus or minus 1. They're superpositions of north and south pole with a certain phase and the normalization. And they're eigenstates of the x operator with eigenvalues plus 1 and minus 1. And the z operator is now the thing that flips them, right? It's just applying Hadamards everywhere to interchange x and z, basically. And so 0 logical is plus, plus, plus. 1 logical is minus, minus, minus. X logical is 3 z's. Z logical is 3 x's. And if there's a phase flip error, if I apply a z to the middle guy, it changes plus to minus and minus to plus. So now it's all the same as before, except it works for phase flip errors. And so now Peter Shor developed, who gave us error correction, among other things, took this 3-qubit bit flip code and then made 3 copies of that as a phase flip code using a total of 9 qubits. And here's the logical states. Here you see the superposition of bit flip code states that's sensitive now to phase flips. And this will correct a single bit flip or phase flip or both, it turns out, if they're on the same site, namely a Y error. A single Pauli error on the 9 physical qubits. So it's NKD. N is 9 physical qubits, 1 logical qubit, and the distance of the code is 3. If I flip all 3 bits, I get a minus sign on this guy, so that's a logical phase error. If I apply z to all of these, I interchange 0 and 1, and it's a logical bit flip.
So what does that mean, 0 bar, 1 bar?
That just means 0 logical and 1 logical. I copied this out of something that used a different notation. So remember, the logical operators are XXX and ZZZ. So if I have 3 errors, that's just a logical operator applied to my system. It looks like no errors, but now I'm wrong. Okay, so this is like the next most complicated code. And then you'll hear this week about other codes. And you'll hear about bosonic codes where instead of using qubits, we use microwave resonators that hold 0, 1, 2, 3, 4, 5 microwave photons and superpositions of those in one single object, an aluminum box at low temperature just holding photons. Instead of having 3 or 9 qubits, we have one object. Those are called bosonic codes. Okay, so are we there yet? Well, there's sort of this stairway to fault-tolerant quantum computation, and we've learned how to make work on multiple physical qubits, make very accurate measurements and control. We've just now, error correction is beginning to make logical memory a factor of 2 or 2.5 times longer than the error correction gain is 2 or 2.5. We need it to be 1 billion, but at least it's above 1 now. And so we're kind of here learning how to do operations on logical qubits. You know, you've got this logical qubit that has, I don't know, 55 qubits in it. How do you do a gate on that? It's something very complicated and may take you a lot longer than it did to do it just a operation on a single qubit. So the lifetime has to get more long than you think to get real gain, which is the gain not just in the lifetime, the memory, but how many gate operations you can do. If the gates are slower, that's a penalty. So this is really, really hard engineering challenge. But we're sort of just entering the age of error correction and early stages of fault tolerance. So we need to get error correction gain for memory and gates much, much bigger than 2.5. But you know, we're just entering an era where things are changing very rapidly, both for superconducting qubits, trapped ions, and Rydberg neutral atoms. And I think that's the end, so happy to take questions.